Hi, we're Ene, Eric, and Eduardo, the 3E team. In this video, we'll show you the progress of our project developed in Seminar 3. Mexico is facing a severe water crisis exacerbated by climate change, the overexploitation of aquifers, and a lack of infrastructure. By 2024, 75% of the country will experience some degree of drought, affecting both urban and rural areas. In Mexican households of 4 people, up to 150 liters of water are wasted daily due to bad habits such as letting the water run while waiting for it to heat up during a shower. According to the EPA, 20% of the water in a shower is lost in this process, which equates to nearly 19,000 liters per year per family.
During Seminar 1 and based on the methodology described in the book on design and development by Ulrich and Ettinger, we are able to establish the product description. Modernization of the shower system for homes, for installation in the exposed pipe of the existing shower system, reduces the time of hot water output when the tap is opened at the start of the shower, reduces water consumption and has an efficient, adjustable and comfortable pool. This description identifies the basic function of the product, avoiding implying a specific product concept, and which we see as a statement of the vision of what the product should be. Below is the table with the identification of customer needs that we obtained throughout the seminar.
In Seminar 2, we carried out the target specification. Here, we worked to determine the metrics based on user needs, along with conducting the benchmarking. We also classified the metrics by level of importance, in order to understand which ones we want to excel in, which ones we want to be among the leaders, which ones have an acceptable average performance, and which ones may not be as necessary and could be left unmet. At the end of the process, this gave us a clear vision of the metrics we must meet if we want to generate differentiation in the market. We also carried out the problem decomposition process, where we applied the clarify the problem methodology through functional decomposition by sequence of user actions, and decomposition by key customer needs. It is important to mention that during Seminar 3, we worked in more detail on clarifying the problem, which allowed us to refine the subproblems identified in Seminar 2 with greater precision.
This seminar covered the stages of concept generation and selection. The concept generation process involved internal and external searches as well as systematic exploration. Subsequently, techniques such as multi-voting, concept screening, and concept scoring were applied to identify the ideas with the highest development potential.
These are the critical subproblems we've identified and will be addressing throughout this presentation. We met as a team to conduct an internal search, using our individual and group knowledge of the project to generate ideas. It's important to mention that we sought the greatest possible creativity in brainstorming, so we tried to be as thorough and creative as possible to tailor the information to each subproblem.
For the concept generation process, both internal and external searches, we used a variety of tools that helped us boost creativity, generate different or disruptive ideas, and refresh our minds to visualize concepts we might not have considered without using these tools. Here you can see the tools we used.
Throughout the internet search, we relied on different methodologies to generate new ideas. These were very helpful in giving us a new approach to each subproblem. In this first critical subproblem, we use the methodologies: direct analogy, what if, provocation, scamper, affinity map, and roleplay. As it was the first exercise carried out, we obtained a greater number of ideas. It is important to mention that the team's focus was to detect ideas that could help us in solving each subproblem. So in some cases, if we put how, it would look in our system. In other cases, they are only the idea. By using these methodologies, we were able to realize 42 new ideas for this critical subproblem. In the process of generating ideas for this critical subproblem, maintaining the desired water temperature constantly throughout the shower, the methodologies were used and 29 ideas were achieved to attack this subproblem in different ways. The same is true for this critical subproblem. We try to use methodologies to generate ideas while simultaneously focusing solely on generating ideas. These ideas will then help us solve the problem and visualize how it will be integrated into the system. Applying these techniques has allowed us to explore a wide range of solutions to the critical subproblems of our shower system. We have learned that diversity of approaches, suspension of judgment, structuring the analysis, iteration, user focus, and consideration of feasibility are key elements of a successful innovation process. We managed to generate 30 new concepts. Each technique offers a unique perspective and stimulates different types of thinking, in addition to suspending critical judgment. This allows for greater fluidity of thought and prevents premature criticism from inhibiting creativity. In searching for solutions, it was important to be open to exploring ideas outside the direct context of the problem. This encourages both conventional and disruptive brainstorming. It was crucial to create an environment where all ideas were welcome, even those that initially seemed far fetched. We managed to realize 23 new ideas in the product development and process improvement process. Gathering external information is a key step for identifying existing solutions, understanding market trends, and evaluating applicable technologies. This presentation explored the importance of external research and its benefits derived from investigating existing solutions and exploring new alternatives for our critical subfunctions subproblems. The suggested strategies for collecting information from external sources are as follows: interview main users, consult experts, search patents, search published literature, evaluate related products, use the Oxford TRIZ effects database. To address this problem, solutions have been explored through biomimicry, patent analysis, review of existing products, and innovative strategies in the industry. Nature offers efficient mechanisms for the movement and storage of liquid. In parallel, systems have been identified on the market and in patents, allowing us to evaluate an approach to generate ideas to solve this subproblem. 41 new concepts were realized. 20 new ideas were made for this subproblem, highlighting the research patterns as they give us a perspective of what we can innovate in our project. 32 new ideas were developed for this subproblem, highlighting products related to patent searches. This gives us a new perspective on solutions we hadn't considered, as they give us insight into what we can innovate in our project. By exploring patterns in biomimicry, we identified previous innovations that could be adapted or combined with our design. Evaluating related products allowed us to analyze existing configurations, their advantages and limitations, which helped us establish optimization criteria. One of the most significant lessons learned from this process was the importance of leveraging existing solutions whenever possible, which allowed us to focus our efforts on unexplored solution areas that could represent an innovation for our project.
During the internal and external search stage, we used the selected tools, TRIZ, corresponding to external search, bisociation, corresponding to internal search, biomimicry, corresponding to external search. This process was corrected as we had initially omitted some important steps within each tool. After making the corrections, we obtained concepts for the four subproblems using the three tools. The feedback from the doctors was very valuable for the proper correction and execution of the tools. Carrying out the correction allowed us to increase creativity, taking advantage of the knowledge we already have about the problem, the market, the established needs, metrics, etc. The objective was to foster ideas using our knowledge, experience, creativity, and internal resources. In this first stage, the TRIZ process was carried out, starting with the identification of the characteristic we wanted to improve. Then, we defined the characteristic that needed to be preserved without compromising what we aimed to maintain. Using the technical contradiction based on the official TRIZ matrix, both aspects were cross referenced to find the applicable inventive principles. From this process, a conceptual solution was developed that resolves the technical contradiction without sacrificing functionality or efficiency. This process was applied to all four critical subproblems. In this process, Interesting ideas were obtained, such as a mechanism that transmits pressure through a mechanism activated by the person's weight, or also a system that automatically adapts to the inlet water conditions without manual intervention, etc. Using the TRIS tool, we generated 5 concepts for the first subproblem, 4 concepts for the second, 11 concepts for the third, and 5 concepts for the fourth. This resulted in a total of 25 concepts generated using the TRIS tool. In the next stage, we used the bioassociation tool, in which we applied the process of connecting ideas from two different fields, that is, contexts that are not normally related, with the aim of generating a new concept. We aimed to break traditional mental patterns, which would allow us to generate completely creative and innovative concepts. The first thing we did was select the problem. Then, we identified two unrelated areas by analyzing processes, structures, or principles, all with the goal of creating a new concept. Here, we present some of the concepts that were generated. For example, a pressurized tank that is incorporated into the shower head. This tank can be air refillable or self-filling. And also, the following concept: a hydraulic press that allows the pressure to be pre-calibrated and adjusted when necessary by the user. And manual pressure adjustable sprayer nebulizer. Using the biassociation tool, we generated 5 concepts for the first subproblem, 4 concepts for the second, 6 concepts for the third, and 5 concepts for the fourth. This resulted in a total of 20 concepts generated using the biassociation tool. Finally, we used the biomimicry tool, which helped us generate more concepts by encouraging us to think about functions that nature could solve. To do this, the first thing we did was identify the function we needed. Then, we used the platform asknature.org to search for biological strategies. After that, we extracted the design principles, translated from natural solutions, into principles or strategies applicable to our design. We then used the extracted principles to create a design aimed at being innovative and functional. We would like to share some examples of the concepts that were obtained using this tool. Using the biomimicry tool, we generated 6 concepts for the first subproblem, 5 concepts for the second, 5 concepts for the third, and 5 concepts for the fourth. This resulted in a total of 21 concepts generated using the biomimicry tool. In the concept classification tree stage, what we did was organize all the concepts from the 4 subproblems into a table. Then, repeated and similar concepts were grouped into a single subproblem. In the first subproblem, a total of 71 concepts were created, in the second, 60, in the third, 81, and in the fourth, 46. To make the work easier, we created codes based on the different methodologies, and we also reduced the concept descriptions to more specific ones. This helped us begin the classification process. It is important to mention that the process helped us identify some branches that we had not previously considered at the beginning of the concept classification tree execution. For each subproblem, we divided the concepts into categories, creating branches that extended to 2 working groups. This process helped us reduce the complexity of the concept generation activities and also allowed us to identify some healthy competition among the concepts. Therefore, this stage of the method helped us to ensure a complete exploration of the solution space, prevent all ideas from clustering around the same line of thought, facilitate the comparison and combination of more diverse concepts.
After conducting internal and external explorations to generate concepts that would solve our 4 critical subproblems, we built classification trees. This tool allowed us to categorize the solutions and eliminate the least promising or repetitive ones, thereby reducing the number of proposals from 260 to 31 with the greatest potential. To facilitate visualization of these trees, we assigned each solution description an identifier composed of the critical subproblem number, the idea generation technique used, and a consecutive number as illustrated in the example. Critical subproblem 4, biomimicry technique, solution 4. Once the most promising solutions for each critical subproblem were identified, a concept combination table was used as a systematic method to integrate them. This table organizes the critical subproblems into columns and shows, for each one, the solutions derived from their respective classification trees. To generate integrated concepts, solutions from different subproblems were combined so that each solution complemented the others, forming complete functional systems. For example, concept 1 was created by combining solution 1 of critical subproblem 1, solution 2 of critical subproblem 2, solution 4 of critical subproblem 3, and solution 2 of critical subproblem 4. This concept is described as a system that allows water recirculation using a module that detects pressure and temperature changes. As it passes through the mixing system with sensors, the cold water is diverted by self-contained pressure pumps. In this way, the 22 generated concepts integrate partial solutions from each critical subproblem, forming coherent and viable proposals. These are 12 of the 22 finalist concepts. They include systems that mix water with hot air, some with tanks to store cold water, and another with a magnetic induction heater. Other concepts are shown here that propose the use of static mixers with induction heating, infrared air heaters, and small tanks that maintain temperature using sensors. Other concepts were also developed that include water recirculation, thermostatic valves, and sensors to maintain temperature and pressure. Some incorporate a mixture of cold air to prevent overheating. Finally, concepts were also included that included induction heaters with sensors to preheat water from a small tank, water reuse systems connected to the toilet with thermostatic mixing, and solutions that combine infrared sensors, static mixing, and autonomous pumping to maintain constant temperature and flow. Once we generated the concepts we considered viable for development, we implemented the multi-vote technique as a rapid screening method. Multi-vote helped us narrow our list of concepts from 22 to 10. This technique allowed us to focus on those we considered most effective in comprehensively solving our critical subproblems. This technique allowed us to actively participate in the selection process with each team member, who received 7 votes to distribute among the 22 concepts. Continuing with the concept screening stage, the selection matrix was developed. To create it, some of the most important criteria were chosen from the list of needs. Each concept was then compared to the Bosch water heater as a reference concept. Having this reference obtained from the benchmarking process allowed us to evaluate whether the concepts created to date were better, worse, or equal under the criteria we selected. By applying this screening, we were able to reduce the selection from 10 to 6 concepts. To advance to the scoring matrix development stage, it was necessary to define new criteria selected from both our list of specifications and those factors we identified as key differentiators in current products on the market. To construct this evaluation matrix, a clear weighting was assigned to each criterion using the initial steps of the AHP methodology. The result, shown in the table, represents the relative weights of each criterion, reflecting its level of relevance within the selection process. Using the weights assigned to each criterion, the relative performance of the concepts was evaluated using a scale of 1 to 5, where 1 indicates significantly lower performance than the reference concept, 3 represents equivalent performance, and 5 reflects significantly higher performance. For this evaluation, several reference concepts were used, selected for their outstanding compliance with certain key criteria. These reference values are identified in red in the table. As a result of this analysis, concepts 7 and 17 were highlighted for their high potential for future development. To corroborate the result, the team decided to use the analytic hierarchy process, which allowed us to corroborate that the result coincides with the concept scoring matrix. Following these evaluations, two finalist concepts were selected. Although concept 17 was identified as the most promising at this stage, other proposals that could complement it are being considered. A further evaluation could modify this result in the future. Both solutions stand out for their innovative heating systems that differentiate them from existing products on the market. While a sufficient level of detail was not developed to describe the specific operation of the heaters, it is clear that both require electrical power to operate. Furthermore, all concepts were conceived with the premise of installation in exposed piping, either in the handle area or near the shower head. Overall, applying these screening and selection techniques in a structured manner was key to reducing emotional bias and ensuring a more objective selection of the finalist concepts. There is no doubt that this stage was arduous and complicated. From the constant generation of concepts to the screening and scoring to arrive at the two finalist concepts, this seminar was an exciting journey where we observed how the process converges to obtain results with greater possibilities of development. The team recognizes the potential for combining and improving current concepts. Therefore, we hope to have more refined models before the next seminar, which will serve as a basis for initiating Seminar 4. We have high expectations for the next seminar with the goal of converging on a single concept. This concept will allow us to apply and develop the knowledge acquired in systems architecture and other subjects, thus refining the selected design. We greatly appreciate the learning and guidance provided by the instructors. Thank you.